So today's topic is statistical testing. Just as a very quick recap of what we talked about last time. Really important to understand this thing. We in the last week and the previous section talked about the sample variance, sample mean, and the way we use them to come up with confidence intervals, which are kind of like intervals which give us an idea that, yeah, if this distribution is what it's supposed to be, then the expected value will be within this range with 95% confidence. It's not the same as 95% probability, because it says that, okay, if we have a expected value, then the confidence interval around that expected value, 95% of the time it will contain this value. And there were different versions of that. And then there was also the confidence interval for variance, which basically had the sample variance the same way. We had an idea that, okay, this is the sample. We calculate the sample variance, and under the assumptions that yeah, this is pretty much more or less the chi-squared distribution, like the sample variance should be, when normalized. Then this is the sort of stuff that, yeah, if this is so, then in this interval, the sample variance will be within this range 95% of the time. Well, 95% of the time, this interval will be placed in such a way that the true variance is between those two values. So confidence intervals can be used, for example, to say that, okay, it's give or take this much. So when you see like a poll of results, and then usually what they say is that the error margins are this and that and so forth, and then usually they use kind of confidence intervals and things like this. I mean, it depends. I mean, usually when they have it, they just state something and it doesn't actually mean anything. They say that, okay, the error margin is 0.5 units or something like this. What they really mean is there is some kind of confidence interval going on, but you'd have to check their actual paper to see which kind of confidence intervals they mean. All right. Well, an alternative way to look at things is to do what is called a statistical test. So what does a statistical test mean? Well, firstly, the idea here is that we postulate a hypothesis. So in all sciences, a hypothesis is a statement about something, and it's meant to be either true or false. Like, I have a hypothesis that the sun will rise tomorrow morning. That's my hypothesis. It will turn out either true or false. And I will test my hypothesis by waiting for, I don't know, about 18 hours or so. I don't remember when the sun rises, maybe around 6 o'clock or 7 o'clock in the morning. I wait for that many times, and I observe the sky, the horizon in the direction of roughly east or somewhat southeast. And if I see the sun, then my hypothesis turns out to be true. This is my test of the hypothesis. So the hypothesis is the sun rises tomorrow, and my test of this the test of this hypothesis is true. I mean, it's a successful test. Turns out to be a true hypothesis if the sun actually rises in the morning. I set some criteria on when it's true and when it's not. A statistical hypothesis means that we postulate a property of the distribution. So we say that, all right, I use this drug on people, and I look at the outcomes of what comes out. And there are some people who receive the placebo, I just give them calcium tablets or something that doesn't have that drug, and another group of people, I give them that drug. And then I look at the distributions of symptoms, for instance, after a couple of weeks of treatment. And I postulate a hypothesis saying that usually my hypothesis is something like the expected number of people who recover with the drug is the same, is not bit any larger than the proportion of people who get better when they're not given any drugs. So this is like the expected value. Let's say that I have some hypothesis like a proper probability of people being cured of the disease if they receive the drug, and probability of a person being cured of the disease if they don't receive the drug. And my postulate is that the drug treatment is no more effective than not treating them. So of course, there's certain probability, with certain probability people get better. I give them the drug, and my hypothesis is that these two probabilities are the same. So this boils down to the distribution having a certain expected value. So I have an expected number of people who get better, and I have another expected number of people who get better. And I say that these two distributions are the same. For example, so this is a statement about the expected value, or it could be a statement about variance or something else. In this chapter, we talk about two kinds of hypotheses, statements about variance or variances of two different distributions, or you know, differences between distributions in terms of expected value and variance, but they could be any other statistics that we calculate. Those kind of tests then turn out to be somewhat harder, but these tests I will explain. So this is introduction to statistical inference. So, you know, we only cover a couple of these tests. And by inference here, we mean, okay, when we carry out the test, we infer that the hypothesis is either true or false. And how do we infer it? Well, we administer what is called a test. And that means that we take a sample of the distribution and come up with a probability that this is interpreted as likelihood of the hypothesis of being true or false. So, for instance, if I hypothesize that the expected value is 0, I take an average of a large group of people, and I get a sample mean of 10. My hypothesis may be true or false, and of course it depends on how rare this kind of event should be. And that depends on the variance, of course. I mean, if the variance is very high, then a sample mean of 10 may very well be something that is very probable, even if the actual expected value is 0. But if the variance is very small, like the variance is 1, and I get a sample mean of 10, then the expected value probably is not 0. So I don't get a definite yes or no answer. Instead, I get a probability that is interpreted as the likelihood of the hypothesis being true or false. And it must be separated. It's not the probability the hypothesis is true or false. It's actually the probability of getting a result such as this if the hypothesis is true. So let me explain it in more detail. So common approach to testing is we have basically two hypotheses. The null hypothesis, which is a conservative, business as usual, everything is normal, there are no differences, that sort of stuff, null hypothesis. And then there is the alternative hypothesis, which is like, you know, yeah, there is a difference and this one is bigger, or there is a difference that this one is smaller, or there is a difference, this is not 0. There is some effect, for instance. The test itself is carried out with the assumption that the null hypothesis is true. So we assume, simply assume that the null hypothesis is true. So when we do let's say a double-blind experiment on a drug, we assume that the drug doesn't work. It's very important that this assumption is made. If the result then indicates that this null hypothesis is false, it is rejected. Well, what does it mean that it indicates that the null hypothesis is false? It says that we get significantly, and I'll explain shortly what that means, but we get a significantly larger proportion of people getting healed or cured if they are given drug as compared to the group of people who don't receive the drug. Hypothesis test in itself is a random variable, and it is susceptible to interpretation error. So we may interpret what is simply a random result as, yeah, this proves that the hypothesis is false, where in fact the hypothesis is true. Usually the hypothesis that we reject or try to reject, the null hypothesis, is usually such that the drug doesn't work. So we reject that hypothesis, and the alternative hypothesis being, yeah, the drug does work, is accepted. But there is an interpretation error that can be made. We may interpret a purely random situation as simply being a result of the random result, we interpret it falsely as something that, yeah, this was null hypothesis was rejected. But then when we carry out the test again, we get a completely different result, and we are puzzled. How is this so? So the conclusion of the test, I mean, I focus on how it may be wrong, because it's really important to understand that even if we end up carrying a successful test or proving or testing some hypothesis and rejecting the null hypothesis, we may be doing it wrong. Alternatively, we may be accepting the null hypothesis even when it's right. So there are two types of errors. One, we reject the false positive. We reject the null hypothesis even though it's true. So this is quite common in layman's terms. You know, people do this. They reject the null hypothesis even though it's true. Like, for instance, they say that, yeah, I know that homeopathic medicine works. Well, how do you know? I have a friend who went to take some homeopathic medicine. He had before taking it, he had a serious headache, and after taking it, you know, he was well again. Well, it doesn't work, and they rejected the null hypothesis that it didn't work, even though the null hypothesis was true. The other possibility is false negative. Well, this could be like saying, you know, my null hypothesis is accepted even though the null hypothesis is false. So, you know, maybe, you know, you go to see, I don't know, I'm not a football fan, so this is just a joke, but let me give it as a joking. It says, you know, you go to see, what would be your favorite, someone's favorite football team? Like, you go to see the Bayern München match. And all hypothesis is that they're not really the greatest football team in the world. And they lose. And yeah, you accept, yeah, they're not the greatest. But they are the greatest, because I'm not sure if they are. I mean, this is just an example. And they end up winning every other game, and they are the greatest. You just happen to reject it because you had a very small sample there and you took the false negative. So what is the lesson here? We want to figure out how to control for these kind of errors. But the problem is, we can only make assumptions usually based on the null hypothesis being in fact true. Because usually we cannot actually assess the probabilities pertaining to the assumption that it's false. So usually the null hypothesis is something which you know, in the context of which we can assess probabilities. So for instance, if the drug doesn't work, then these two populations should have the same sample mean. I mean, the sample means should be close. They have the same expected value of being cured of the disease, whether or not they are given the drug. Okay? So the null hypothesis gives us certain probabilities. But if the drug works, we have no idea how large its effect is, right? We don't know. We have no way of knowing that even with this test. I mean, this test may provide us with some idea, but it's still, you know, before we administer the test, we have no idea. So we cannot afford, you know, before the fact, we cannot formulate the probabilities under the hypothesis, the alternative hypothesis. This is what you need to understand. The null hypothesis is the hypothesis that everything goes the same as usual, or everything performs as per some simplistic random model. And then we can formulate the probabilities of certain events. And then, you know, we can assess what we call a risk. So the risk level or significance of the test can be determined, and it can be controlled by this type 1 error. So the idea here is that we look for events that have a small probability of happening if the null hypothesis is true. The problem with this is that if the null hypothesis is true, then sometimes rare events happen. But that's something we cannot, that's something we can't control. So commonly we may use, I mean, in old school hypothesis testing, what we do is we formulate a predetermined risk level, but it's not really necessary. So we may end up with 0.05 or 0.01 or 0.001. Actually, when you use some software that calculates tests for you, they usually have this star notation for the tests. So it's 1 star if it's between 0.05 and 0.1. It's 2 star if it's between 0.01 and 0.001, and it's a 3 star significance if it's below 0.001. So usually these 3 are usually used in software. So if you carry out statistical tests that using statistical software, they usually give you this star notation about significance, or in papers, it's very common to denote by stars, you know, the significance. So if you statistically do the test and you know, if it passes these different levels of significance, then it's given a certain number of stars. And if it's no stars, then it doesn't pass any of these tests. But it doesn't really matter, because what we are calculating is a different value, and we then compare it to this alpha. And that's the result of the test. Well, the hypothesis setting's nature prevents us from really calculating the alternative hypothesis probability. Look, if this is if H0 is true and we reject it, then the probability, this type 1 error, is what is going to happen. We choose something. So if the event that the probability of event, let's say we choose this 1 in 1,000. So if H0 is true, if our null hypothesis is true, then once every 1,000 tests on average, when we carry this test many times, then 1 test in 1,000 on average tends to fail, meaning that we get a rejection for that. But we have no idea about this, what happens. I mean, do we accept it even if the, sorry, even though the hypothesis is false? Usually this zero or null hypothesis is the ground assumption of the model that we are using. If the model is correct, then we can say how probably it produces anomalous results or results that are very large or very small. But if it's wrong, we don't know how and why it is wrong or how it's false. Only two things we can say for certain, because we don't know the beta. Alpha we can set, but beta we cannot. We have no idea what beta is. The only two things can be set for sure. If we have a sample size that is fixed, then lowering the risk level of type 1 error increases the risk level of type 2 error. So if you want to be sure that you don't reject the null hypothesis when it's true, then you will be sure you will accept it when it's not, right? Because if you set the risk level to 0, then nothing will pass the test. So you have to set it somewhere. And the lower you set the bar, the greater the risk of rejection, accepting the null hypothesis when in fact that null hypothesis is false. The good news is if you increase the sample size, then both types of error probabilities go down. So if you set the alpha very low, then you make sure that your sample size is very big. Okay. Let's put some more meat on the bones, so to speak here. What does it mean? Usually we assume that we are going to present a hypothesis about a parameter of a distribution. And in our case, that would be expected value of variance. Later on, I mean, if you carry on this study, then there will be other kinds of parameters. For instance, you can come up with a hypothesis about regression, so-called regression coefficients. Regression coefficients are measures of you know, how two things are related to one another in a linear fashion that generalizes from correlation. I'm not going to go there, but these coefficients will have their own distributions, and you can assess you can create null hypotheses or hypotheses regarding those coefficients. And there are various other statistics that you can calculate, but we focus on this course on sample mean and sample variance. Oh, and expected value and variance, you know, as the true parameters. Often, like for instance, in my drug test, I mean, I have the null hypothesis that the group with the drug administered has the same probability of being cured as the group with no drug administered. So these two probabilities are the same, or the expected number of people being cured is the same as without the drug. And the alternative hypothesis would then maybe that, you know, if it's not, then the drug helps. Or if it's like, you know, using seat belts prevents deaths in car accidents, that would be null hypothesis would be the seat belt is useless. The alternative hypothesis would be that the seat belt actually helps. You know, it could also be just that these two things are not the same. Like for instance, you have a group of people who take a test, and you have another group of people who take the same test. And your null hypothesis is that these two groups of people do exactly the same. But you have no preconception about which does better. So your alternative hypothesis is that the results are different. So given a risk level alpha, we test the hypothesis by finding the confidence interval, basically. And depending on which way we formulate the alternative hypothesis, we could just find the upper or lower bound of the of the confidence interval. So basically, this is what we do. We calculate the confidence interval to carry out the test. And then we check whether the hypothesized expected value or the hypothesized variance or whatever the hypothesized parameter is, whether it falls inside that confidence interval. If it does, then the null hypothesis is assumed to be true. And if it doesn't, then we reject the null hypothesis. Simple as that. So the way we carry out the test, we calculate the statistics T. So this could be sample mean, this could be sample variance. This could be some other thing that we calculated. We have some function of the sample, and we have to define the test statistic in such a way that we know the distribution of this test statistics if the null hypothesis is true. So we kind of assume the null hypothesis is to be true, and then we calculate that, okay, if we take this average from this, the mean or the sample of this distribution, calculate the average, then, you know, the average has expected value that is the same as this assumed thing, the one that we assume, this distribution, it has the same expected value, and the variance is that variance divided by n, because we have n, and so we can formulate it, and then we can calculate the distribution of this test variable. And when we calculate the critical region of this, we calculate, okay, if this is the distribution, that the sample mean will land with probability alpha within this range of the actual expected value. And in order to minimize this beta, we usually choose it in such a way that this, if it's just about difference, we choose it that the expected value is smack at the middle of this region. If the alternative hypothesis is that you know, it's that drug helps better than this, then we only rule out the part where more people get you know, in this region, more people get cured than on average, and in here, the same or fewer people get. So we have this distribution, and here is the region. So if the value tends to land here, we conclude that, yeah, it's actually better. If we land here near the average is right here. So if we land, or the expected value is here, if we land here, then we assume that, okay, this is where, this is the null hypothesis territory, and here the alternative hypothesis territory. Let me draw a picture. I think it's better that I draw a picture. So here's my distribution of how many people get cured if there are no differences to people who actually go. So we look at the statistics. Let's say we've taken a lot of statistics. We've taken from the literature. We know that a certain disease, you know, cures itself. People get cured within 1 week with probability of 0.7. So if we take 1,000 people, then we would expect that 700 of these people are going to be cured within 2 weeks on average, right? So 300 remain sick even after 3 weeks, or 2 weeks. So when we calculate the average, we take 100 people, and we have here is the mean is 700, and 700 who are cured. Of course, the maximum here is 1,000, let's say. So it's actually 0 between that. And we calculate that if more than 900 get cured, then we get something like this. If we land in this region, then we deduce that the drug is actually helpful. But if we land somewhere in here, we conclude that the drug didn't help because it could be just any number between that and that. So the alpha basically is this region. So if we say that if the average is this 700, if the, this expected number of people getting cured is 700, we know this distribution. I don't know what it is, but we calculate what that distribution is from let's say, I don't know, medical records or something. And then we give the drug to 1,000 people who are sick. And after 2 weeks, we look at them. And we determine that, yeah, with the distribution of the pattern of how people get cured, it looks like if we set the probability is about 5% that 900 or more get cured, or 0.01. So it's 1 in 1,000 probability that this many get, more than 1,000 get cured. So if sorry, more than 900 get cured. So if we get 920 people get cured, it lands here, so we reject the null hypothesis. The drug makes a difference. On the other hand, if we have 790 people who are cured, we conclude that, okay, it could be just a randomness contributing here, and we accept the null hypothesis that the drug doesn't do anything. Why we choose this this region here and not this other region here is that because we want to minimize the type 2 error. We have no reason whatsoever to assume that the drug makes things worse. So if we get this unlikely event where it's actually better, then that's good. We don't want to reject it needlessly. So we don't choose these things, or we don't choose the 5% at the middle here. We choose the 5% at the edge here, where the alternative hypothesis is more likely to be true. Of course, alternative hypothesis is more likely that the drug helps is more likely to be true in case more people are cured. That's why we choose that region, to minimize the beta. So the test is either one-tailed, which is in this case, or two-tailed. Two-tailed meaning that let's say we are comparing a group of people to the average, and we don't know whether they do better on the test or whether they do worse. Or we don't know if this group of people is taller or less tall than average people. So if we don't know if it's bigger or smaller, then we use the two-tailed test. And in this case, we take the alpha region to be the edges of the distribution. So for instance, let's say this is the height of people on average. Here's the average height. Then we choose these regions in such a way that our alpha probability resides on both sides. So we measure people's height in certain, let's say in a certain region, and our null hypothesis is that they are the same height as everyone else. But it turns out that either they are shorter or they are taller than average. We don't know which is going to be the alternative hypothesis, but one of them is the alternative hypothesis. So in this case, we just reject the null hypothesis if it's far away on either end. So they're not the same. Something in here is affecting the people's height. So somehow they are either taller or shorter than average. Here are examples. So you have to understand that this curve is formulated under the assumption that the null hypothesis is true. It's really, really important to understand that this curve, these probabilities come from the assumption that the null hypothesis is true. So if let me draw something here. So I have no idea what the actual distribution is under the assumption that the null hypothesis is not true. But let's say that that distribution, that it could be something like this, right? That could be the alternative hypothesis. So the thing is, that's my alpha is there. Sorry. Let me draw this. So if I do this, then this red shaded region here, that probability there is the beta, right? So in order to understand the two types of error, we can control for this alpha, but we cannot control for this beta because we don't know what this red distribution looks like. It's even worse in this figure 2 because we have no idea. The distribution could be to the left or could be to the right. It's just that we assume that it's somewhere else. So the thing is, we have no, this red is like an imaginary distribution. We have no idea what it is. We have no way to formulate what that distribution is, but we know this H0, that's the null hypothesis. And under the null hypothesis, we have this alpha. And in this picture that I just drew, you can easily see that if you decrease the alpha, meaning that you move, if you move this alpha in that direction, then the beta will increase, and conversely like this. But what happens is that if you increase the sample size, and now think about this as a hypothesis about expected value, for instance, then if we increase the sample size, then what happens is this distribution will compress. The peak will become sharper. And then in this case, both the alpha and the beta will become smaller because let's say if I'm going to make the sample size bigger, then this will become something like this, right? And the alpha will now be, the cutoff limit will now be there. So increasing the sample size, and if I look at this new beta, I'm going to use green here. So if I decrease the sample size, oh, that's not a good color. Let me use some other color. Let me use red. So you see that increasing the sample size and keeping alpha the same, the beta will decrease. And you can you can decrease both alpha and beta if you have the same sample size. Then you can sorry, if you increase the sample size, then you can have a larger alpha yet smaller alpha and yet smaller beta too, right? So I hope this figure helps you understand it a little bit better, what is going on with these risk levels. We don't know what the beta is, but the point here is that increasing alpha will make beta smaller and vice versa, but increasing sample size will make both of these smaller. Allows both of these to be made smaller. All right, let's move along. The test statistics, which is usually it's either the sample mean, sample average, or something like this. We calculate the value and compare it to the critical region. If the test statistics falls in this region, we null hypothesis rejected. So basically, if we get a test result that is in this shaded blue region in the one tail or the two tail test, if it's in this shaded blue region, our result, then we reject the null hypothesis. And if we don't, well, the null hypothesis remains in place. The result may be indicated by giving a p-value of the test. The p-value, the smallest alpha that would result in rejection. So let me just explain. If I get a new value, I'll just draw here a picture. So if I get, well, that's not a good. Let's say that I get this value here. Then the p-value is the probability that remains in the tail to the left of this value. That's the p-value. And if the p-value is very small, then very little probability remains on the left-hand side of this value. So the p-value is the smallest alpha that would result in rejecting the null hypothesis. Usually if the p-value is greater than 0.05, then we have not rejected the null hypothesis, and those are not considered to be statistically significant results. So here's the summary. Let's have a small break. I don't have group work for you guys now, but I would like you guys, I'm going to pause the recording. Right, we have resumed recording. So we're going to be testing the expected value now. There seems to be a typo in that maybe some problem with the LaTeX. I may have edited it somewhere along the line. So this should be X, and then we have this arrow, and then there should be this. There's probably some kind of tag missing there, and this results in this. So we know that the sample mean has the normal distribution with expected values mu and variance sigma squared over n. This can be assumed. If the sample is large, we can assume this even when the original distribution is not normally distributed. However, we should be very wary of doing so with a sample size that is somewhat large. Like if we have a 20 sample, then if we have a 20 n is 20, the sample is not really normally distributed then. If it's 2000, then yeah, but you know, and it all boils down to different assumptions about the distribution. We can't really go into great detail here, but you know, be wary of this. So these tests are pretty good if the original sample comes from a distribution that is normally distributed or close to being normally distributed, or if the sample size is very large compared to how badly it is distributed. We calculate again the normalized variable, which we take to be, let's say, the z, to be the sample mean minus the hypothesized expected value over the known sigma over the square root of n. So in this case, this would be 0, 1 normally distributed if the null hypothesis is true. Right. So here we use the null hypothesis. Choosing this mu 0 here, and assuming that this is normally distributed with this 0, 1. This is then using the null hypothesis, and all this is under the null hypothesis. This is our test statistics. In this case, is this z value, this normalized. Now we calculate in a similar way as we calculate confidence interval. We calculate the confidence interval around the hypothesized expected value. So, so if our depending on how our null hypothesis goes, sorry, our alternative hypothesis. If our alternative hypothesis is that mu is, if our alternative hypothesis is that if they're not the same, then the sample comes from a distribution where the expected value is smaller, the critical region is then the negative part of this minus Z alpha, and we just take the p-value to be this cumulative distribution function, normal cumulative distribution function of this test statistic Z. If our alternative hypothesis is that this mu is in fact greater than this mu0, then our critical region is the larger part, the Z alpha part with the positive part, and our p-value is 1 minus this cumulative distribution function of this data, sorry, Z. If our null hypothesis is simply that we are either smaller or bigger, it's different, then we take Z alpha over 2, so this would be the ends of the critical region around the hypothesized expected value. And if it's smaller or larger, this test statistics, then we reject the hypothesis. And the p-value is, now we take 2 times this, because let me just draw a picture. So there are 2 cases. I'll draw you a picture of the 2 cases. Well, I actually already had the 2 cases, but so up here we have the one-sided test. So our null hypothesis is accepted if our Z lands here and rejected if the Z lands here. And this is the second one where, sorry, the first one where these values are small, right? And the p-value, that's our Z. And then the p-value in this case would be all the probability mass that resides on the right-hand side of this. On the other hand, if we have the 2-sided test, then the critical region are these 2 shaded regions here. Half of the critical probability, alpha over 2, is here, and the other half is here, right? Now, if we end up in, let's say we end up here, and we reject the null hypothesis, right? We end up here and we reject the null hypothesis. Then our p-value is twice this region. This, I'm shading it a little bit darker than so the region that resides here, I take it as twice because this Z is big, but it could just as well be small. So this twice this probability here means that it's this or the corresponding symmetric small one here. So it's the probability of landing this far from the expected value. So in the first 2 hypotheses, the first one is the probability of landing in a value that is this much smaller. This one is the probability of landing in a value that is this much bigger or more. And why we use double this is that this is the value of landing this far, either smaller, which would be the, whichever these is the bigger, the smaller one, because if we are at the, this is if we are at the high tail and this is if we are at the low tail. And it's twice that because you include also the probability that you would have ended in a value that is as far but smaller, or you know, if it was a small value, then as far but bigger. That's why you use the double here as the p-value. This is to take into account the fact that your uncertainty was that is there is more uncertainty in kind of more uncertainty here. The alternative hypothesis being that it's different. So it could be different by being smaller or different by being larger. So correspondingly, these critical regions are smaller in these cases, and the probabilities that you receive are smaller, but the p-value is bigger because it could have just as well been a bigger value. All right, here's an example. Annual rainfall measured in millimeters in a given region is a normal distribution, and as expected values 106 millimeters, and with a standard deviation of 15.3. It's usually given using the standard deviation. And we've deduced this from 100-year averages. So let's say that we've done it between 1890 and 1990. And then the last 5 years, the average rainfall has been 89.3 millimeters. Justify your choice of alpha and test whether it is reasonable to conclude that, let's say, for instance, a climate change has occurred and rainfall has diminished. There is no, well, it's not being done here. It's not done here. So let's do this together, but let's do it in steps. I'm going to pause the recording while you guys discuss, and I'm going to resume the recording when I chip in. So I'm going to resume recording. So I'm going to start here with writing down the necessary variables. So the mu0, this is the hypothesized, the null hypothesis states that the expected rainfall is 106. Or actually, I'll put it at 106.0. Well, it doesn't really matter. And then I put the sigma, which I assume to be the same as a 15.3. This is the sigma. I had the sigma squared as 15.3 squared, but this is lucky. My n is now 5 because I have 5 years average there. And my x bar is 89.3, right? So I'm just going to calculate the Z statistic here. So before I do, you should justify the choice of alpha. So just, and tell me what kind of alpha would you choose? So let's have a short discussion here. We should just determine the risk level. So any suggestions? I'm hoping you will participate. Did you discuss this in the group?
At least my group, we tried to, but we didn't know how to start even, so.
Okay, all right. We have to justify the risk level. So what does the risk level mean? If the null hypothesis is true and we choose a given alpha, what is its interpretation? So let me just, before we carry on, if I choose alpha 1, I just put alpha 1 at 0.05, which was one of the suggestions. What does this mean?
We take 95% confidence.
It's 95% confidence, but hear me out very well. If I put this at 0.05, then how often would I expect, if I get a null hypothesis that is just at the threshold of being accepted or rejected, if I get something that hits pretty much exactly over this alpha level, then what does this mean? How often would I expect, if I administer the same test, then how often would I expect to get a result such as this? That the null hypothesis is rejected, but it's true. What does it mean? What's the probability there? It's 0.05, right? So you said it's 95% confidence. It means that 95 times out of 100, the test will retain the null hypothesis. And 5 out of 100, that's 1 in 20, right? The null hypothesis will be rejected even if it's true. Okay, so what does it mean in this case when we have 5 years measurement? It means that if we take 20 different 5-year periods, then on average, one of them will in fact indicate a rejection of the null hypothesis, even if we take them, even if the rainfall remains what it is. But let's use alpha for now. Let's use this for now. With knowing we have here probability of rejection is at this level. All right, let's formulate the Z statistic. It's now simply X bar minus mu0, right? Just like it was divided by sigma over the square root of n. This is my Z statistic. I get minus 2.4405. Now I calculate the critical region, and one way to calculate the critical region is look for the Z alpha. And how do I do that? Well, the way to do this is to take the norm in of alpha let me just so I have the alpha mu, and the mu should be 0, and it should be 1. Why is there too many arguments?
I think it's because
Maybe
you
use a dot.
alpha 1.
Oh, I used alpha 1. Ah, that's true. So our critical region extends. I mean, we are hypothesizing that the rainfall has diminished, and if it's reasonable to conclude that the rainfall has diminished, and because we're concluding that it's diminished, then we are looking at the lower region here. So if you look at this slides, page 188, the critical region will be the minus Z alpha and then smaller than that. So actually we are taking the norm in of this alpha really. I mean, if we were to calculate the upper region, it would be 1 minus alpha. So we would get this, this would be our critical region would be above this region. And if we were to have the critical region in the case of the two-sided test, we would have here alpha 0 over, sorry, alpha 1 over 2 and 1 minus alpha 1 over 2. We would have this. This would be our critical region, and anything outside this critical region would be what we would consider. Now Z is clearly smaller than this. Z is clearly smaller than this first one, the critical region here. Then we would reject the null hypothesis. Let's calculate the p-value there. So we calculate the norm CDF of this Z, and well, we can, it's a 0, 1, right? And our p-value is 0.0073. So we would reject this at 0.05. We would reject this at 0.01, but we would not reject this at 0.001, right? So how do we interpret this p-value? Well, this p-value we can interpret in one of many ways, but one way to interpret it would be that well, let's do this. As p is, and so one in every 137 5-year period. We take 137 different 5-year periods. If the null hypothesis is true, then only one of these is expected to have this small rainfall. So we're pretty sure that this is at least this is a very uncommon 5-year period, right? This average has been deduced from a 100-year average. So at least this is probably, I don't know of the records, but this would probably be a record drought in 5 years, right? So I hope this gives you the idea on how to do this kind of example. We'll see many more such examples, and I'll show you. They are in the examples and in the exercises. So basically this is, and now we deduce here. This is infer. Let's stop here for a little while. I'm going to return to the slides.
Can I ask a question?
Yes, of course.
I was just wondering, like, I'm kind of confused. I know that this kind of touches on like the past stuff, but like, how do you know when to use like norm inv and when to use like t inv?
Oh, okay. So, look. Okay. That's a good question. So let's go here. Let's do it here. So if I know this z is not, so let's take this as an example. So in this case, here, I know that z has a 0, 1 normal distribution, right? And let's say that I know the value of z, right? Let's say in my example, I calculated the value of z to be, let me just go back. Oh, I have this, sorry. I calculated the value of z to be minus 2.44, right? So let's say that in my case, I have z is equal to minus 2.4. Let's say this is, I know this, I've calculated this z. And I want to know how probable this z is. And I know that it has normal distribution, 0, 1, right? Then I calculate the probability that z is smaller than z is norm CDF of z. This is, I get the probability. So this written here is the example where I'll draw this picture here. It's a little bit, but I draw it here. So this is the situation where I have a distribution that looks like, let's say it looks like this. I have, that's my z, okay? And then this norm CDF gives me this probability of this shaded region, right? Because it's the cumulative distribution function taken from this z. When do I use the norm inv? Okay, here's another example. I'll draw this in red. Here's another example. Let's say now, for argument's sake, that I have this kind of a distribution here. Again, sorry about the bad graphics, right? And here, I know this, and I'm going to write here A instead of alpha because, you know, I'm not, so here, I know this A here. I know the probability of this shaded region. In this case, I would, if I know this A, I've calculated it somehow, then I would calculate the Z as norm inv of A, assuming these are all 0, 1. So the norm inv is just the inverse of the norm CDF. So the norm CDF gives the normal distributions. I mean, in MATLAB, I put I can put the 0, 1 into it. If I don't put it, it's just 0, 1. I didn't put it here, but I mean, you, of course, the additional parameters will be expected value variance if you have additional parameters. If it's not the 0, 1, then you have to input those. So the cumulative, the CDF, be that Poisson, be that normal distribution, be that whatever, it gives you under that, the CDF part, you know, it gives you this probability. If you need the probability of getting a value smaller than that, then you use C. If you know the probability of a lower region here, then you can get the value that is at the edge of that region. You get that value using the norm inv, or the inv of whatever that is. It's the inverse of the cumulative distribution function. Does this answer your question?
It helps a lot, but one further question would be that what's the difference between like, is T-inv for like a different sort of distribution?
Yeah. Okay. We use the T-inv and the T, I don't remember, we usually don't use the student distributions CDF, because we usually only need the T value of a given probability, but the T-inv is used when we don't have a normal distribution, when we have the T distribution. So we use the norm inv and the norm CDF in here because it's the normal distribution, and I'll explain it shortly. We'll use the T-inv and the T distribution when it's the T distribution. So these are the two different cases. I explained it. We can't do it at this session, but next Monday we'll go to the one where we use the T-inv, and we use the T-inv because in that case, when we don't know the variance, then the distribution that we have for our test variable is not going to be normal distribution. Instead, it's going to be the T distribution. And because it's not going to be the normal distribution, we can't use the norm inv and so forth. Instead, we use the T distributions functions. I'll explain that shortly. So yes, you are correct. You use the command you use depends on which distribution you are assuming. So if the underlying distribution was Poisson distribution, you'd use the corresponding function that deals with the Poisson distribution. The ones that we use here are the chi-squared distribution, the T distribution, and the normal distribution. Those are basically the three distribution. Also, I'll show you later, there's one more is going to be coming, and that's going to be the F distribution. So I'll explain those in next week's sessions.
Okay.
Yeah, and if you're confused, then we'll discuss this in depth during the exercises, right? So don't worry. If you're still confused, then I'll help you. That's one of the things that I'll help you choose which function to use.
Just one more question. If you don't know the mean and the variance or the standard deviation, then do you always use like 0, 1? But then you use
the 0, 1 is used. The 0, 1 is used when you normalize. So here we normalize. Look what is going on, what we're doing to this Z statistic here, the Z variable. So we take the original, the things that we assume are known. That's this we assume to be known. That's the expected value. We assume that we know the variance here, right? And then when we calculate the test variable, we normalize it. We subtract from our sample mean, we subtract the hypothesized expected value. In this case, we just assume that we know it. For example, in our rainfall example, this was the long-term average rainfall. Then we have the sample mean, which in our rainfall example was the last 5 years average rainfall. We divided by this statistic to normalize it. This has the original deviation divided by the square root of n. I justified it theoretically because of the fact that the variance becomes divided by n when we have n measurements in our sample. Then we calculate the sample mean, then the variance is the original variance divided by n, and because the larger the sample, the smaller the variance of the sample mean. And now what we're really dividing here with is the sample means standard deviation, which is the square root of the variance. And the square root of the variance is, in this case, the variance is sigma squared over n. So here it's sigma over square root of n. It's the square root of that. And this, under the assumption that the original variable is normally distributed, or under the assumption that the sample is so big that it might as well be normally distributed, then this resulting z variable will be 0, 1 normally distributed. And we use this as our test statistic variable because it's easier to operate here. We don't have to do other calculations to this. We don't have to worry about what this is going to have 0, 1 normal distribution. I hope this clarifies it a little bit.
Yeah, it helped a lot. Thank you.
Yeah, okay. All right, I'm going to stop this recording now. We're going to have the exercise session in about 15 minutes or so. That's how long it takes for this recording to finalize. Thank you for asking this question. We got it on record. I hope you don't mind. It's actually a very good question and it will help others, I hope. And if there are no more questions that you would like to go on record, I'm going to stop the recording now. Right? See you guys next.